Welcome to Quietly Made. I am so glad you have found your way here tonight. This is a space for the curious and the weary, a place where we explore the vast, invisible infrastructures of our world, while giving your mind the permission it needs to simply rest. Before we begin, I invite you to join our community by subscribing and leaving a comment. I often wonder where these stories find you tonight. If you feel inclined, please leave a comment sharing what part of the world you are in and the hour you are settling into sleep. It is a small way for us to feel the quiet connection of this community, scattered across different time zones, but sharing this same moment of rest. If you fall asleep, that is exactly what should happen. You are safe here. You can always come back tomorrow and pick up exactly where you left off. Adjust your pillow. Take a deep, slow breath in and let it out. Let your mind drift as we begin. Before the machine arrived, distance was measured in daylight and the endurance of animals. A journey of 20 miles required negotiation with weather, terrain, and the biological limits of horses whose breath became visible in cold air, whose hooves wore down on stone roads, whose muscles trembled after hours of labor. The rhythm of civilization pulsed at the speed of living things, slow, vulnerable, bound to the earth in ways that shaped every aspect of human planning. In cities, the streets accumulated evidence of this biological transportation system. Manure piled in corners where rain would eventually wash it toward gutters. The smell of stables mixed with coal smoke, creating an atmosphere that defined urban life. Carriages rattled over cobblestones with a particular percussion. Metal-rimmed wheels finding every gap and irregularity, transmitting vibrations through wooden frames into the bodies of passengers who learned to brace themselves against the constant jostling. The limitations were not merely inconvenient, they structured possibility itself. A merchant could only service customers within a radius determined by how far a horse could travel and return in a single day. A doctor's practice was constrained by similar mathematics. Fresh food traveled the distance between farm and market in the time it took for vegetables to wilt and milk to sour. The speed of information matched the speed of the messenger, and urgent news arrived with tired riders on exhausted animals. Within this framework, communities developed a particular density. People lived near their work because the alternative consumed too much time and energy. Neighborhoods formed around the practical range of walking and the occasional hired carriage. The shape of cities reflected these constraints, growing in patterns that accommodated the turning radius of horse-drawn vehicles and the width required for two wagons to pass. Yet, beneath this acceptance of biological limits, a different impulse gathered strength. Engineers and inventors studied the conversion of energy into motion, observing how steam could drive pistons, how combustion could create force, how mechanical systems could multiply human effort. They filled notebooks with sketches of chains and gears, calculating ratios and tolerances, imagining machines that would not tire, that would not require rest or food, that could sustain their pace hour after hour without the trembling that comes to living muscle. The factories themselves demonstrated what was possible when mechanical power replaced animal effort. Water wheels and steam engines turned shafts that never grew weary. Looms operated at speeds no human hand could match. The transformation of production hinted at a broader possibility. That transportation itself might be reconceived, that the fundamental relationship between distance and time might be rewritten by machines that existed outside the biology of breath and blood. In workshops scattered across industrializing nations, individuals worked on components that would eventually assemble into something larger. They refined the metallurgy of gears, tested the resilience of different alloys, experimented with ways to contain and direct explosive force. Each small improvement in materials and mechanisms accumulated like sediment, building toward a threshold that would soon be crossed, though most who contributed to this accumulation could not see the full shape of what they were creating. The streets continued their ancient rhythms, hooves on stone, the creak of leather harnesses, the patient waiting of animals between journeys. But in the margins of this familiar world, something else was taking form, an alternative system that would not complement the old ways, but eventually replace them, altering not just how people moved, but how they thought about space, time, and the structure of daily existence. The hunger for speed existed long before the capability to satisfy it. This was not mere impatience, but a practical recognition that time itself was a resource, limited and irreplaceable, and that its compression through faster movement would unlock possibilities that remained theoretical as long as distance required days instead of hours. Letters took weeks to traverse continents, and the delay shaped the nature of communication itself. People wrote differently when they knew the reply would not arrive for a month. In port cities, the arrival of ships created rhythms that governed commerce and information. Merchants gathered at docks to learn what had happened in distant places weeks earlier, to receive goods ordered before seasons changed, to send responses that would travel back across the same slow routes. The entire structure of trade accommodated itself to these delays, building in buffers and redundancies, maintaining larger inventories because rapid resupply was impossible. The railway had already demonstrated that mechanical transport could shrink geography in ways that reshaped human activity. Where tracks reached, the relationship between places changed fundamentally. Towns that had been 2 days apart by a horse became 2 hours apart by rail, and this compression of distance created new economic patterns, new social possibilities, new expectations about what was reachable within a lifetime. The fixed routes of rail made certain connections while leaving others unchanged, creating corridors of speed through a landscape that remained otherwise bound to older velocities. But the railway, for all its power, was a system of predetermined paths. It connected specific points according to the logic of track laying, which favored the routes that justified the enormous expense of grading land and laying iron. The spaces between the rails remained territories of horse-drawn transport, accessible only at the old speeds by the old methods. A farm 5 miles from the nearest station might as well have been 50 miles away in terms of the benefits that rail travel could provide. What emerged in the minds of engineers and dreamers was a vision of mechanical transport that could go anywhere, that would not require tracks or stations or the coordination of schedules, that could respond to individual needs and desires rather than the planned routes of a centralized system. This was the promise that would eventually be fulfilled by self-powered vehicles capable of navigating existing roads, of traveling point to point without the intermediary of rail networks. The technical challenges were substantial. A vehicle needed to carry its own power source, which meant either accepting the weight of steam boilers and water supplies or finding some other method of generating continuous force. It needed to be steerable with precision, to start and stop reliably, to navigate uneven surfaces without derailing or overturning. Each requirement multiplied the complexity, and early attempts often satisfied some criteria while failing others, creating machines that were too heavy, too dangerous, or too unreliable for practical adoption. Still, the pressure toward solution intensified. As cities grew denser and distances within them increased, as commerce expanded and the coordination of increasingly complex activities required faster communication and movement, the old systems strained under demands they were not designed to meet. Horse populations in major cities reached levels that created serious sanitation problems, and the sheer volume of traffic on narrow streets led to congestion that slowed everything to a pace that frustrated the ambitions of a society accelerating in other dimensions. The need was not uniform. It was felt most acutely by those whose activities suffered most from the constraints of biological transport. Doctors making house calls, salesmen visiting clients, families wanting to escape the density of cities for brief periods, merchants needing to move goods in quantities too small for rail, but too large for a single horse. All of these represented pressures toward a solution that could provide flexible, individual mechanical mobility. The machine that could satisfy this need would not merely improve transportation, but restructure the possibilities of daily life in ways that were difficult to fully anticipate before they arrived. The first self-moving vehicles appeared not as refined products, but as philosophical statements rendered in metal and wood, proof that the thing could be done at all, that human ingenuity could create motion without animal muscle. These early machines were awkward, temperamental, sometimes dangerous, but they represented a crossing of a threshold that had seemed insurmountable. The inventors who built them worked in isolation or small groups, unaware that similar experiments were happening in distant workshops, each solving the same problems in slightly different ways. Steam offered the most obvious path because the technology was already understood. Boilers had been refined through decades of industrial use, and the conversion of steam pressure into mechanical motion was well established. The challenge was miniaturization, taking systems designed for factory floors or railway locomotives and compressing them into something that could fit on a road vehicle while still producing sufficient power to move itself and passengers. The weight of water and fuel, the bulk of the boiler, the need for constant attention to pressure and fire, all of these factors made steam vehicles cumbersome. Yet they moved. Some early steam carriages managed to transport passengers short distances before mechanical failures or fuel exhaustion stopped them. The sound they made was entirely new to city streets. The hiss of steam, the clank of reciprocating engines, a mechanical breathing that announced their presence long before they came into view. Pedestrians and horse-drawn traffic stopped to watch these machines pass, recognizing something unfamiliar, but not yet understanding what it would mean for their own lives. The operators of these vehicles learned through direct experience what would work and what would fail. They discovered that vibration loosened connections, that road dust infiltrated mechanisms, that sudden stops could damage equipment designed for smooth, continuous operation. Each journey was an experiment that yielded data about materials, design, and the practical requirements of road transport. Notebooks filled with observations about how different surfaces affected performance, how various weather conditions impacted reliability, how the human body responded to the particular motions and speeds these machines produced. In parallel, other inventors explored different power sources. Internal combustion engines existed as laboratory curiosities and industrial tools, using explosive mixtures of air and fuel to drive pistons in ways that were more compact than steam, but also more violent and difficult to control. The fuel itself was often dangerous, volatile liquids that could ignite unexpectedly, gases that required careful handling, mixtures that varied in quality and composition. Getting such an engine to run smoothly and reliably required solving problems of ignition timing, fuel delivery, cooling, and the synchronization of multiple moving parts operating at high speeds. The earliest vehicles, powered by internal combustion, were even more temperamental than steam carriages. They sputtered and stalled, produced clouds of noxious smoke, vibrated intensely, and required constant adjustment by operators who needed to understand the mechanical principles involved. Starting the engine itself was often a challenge that required multiple attempts, specific procedures, and sometimes physical strength to turn cranks or prime fuel systems. These were not yet products for general use, but prototypes that demonstrated potential while highlighting everything that still needed refinement. In France, Germany, Britain, and America, this experimental work continued in workshops where machinists fabricated custom parts, where engineers tested theories about gearing ratios and wheel design, where investors occasionally provided funding based on demonstrations that showed promise, even when they also revealed serious flaws. The community of people working on self-powered vehicles remained small, connected by technical journals and occasional exhibitions where inventors could compare approaches and learn from each other's successes and failures. Public reaction to these early machines was mixed. Some saw them as novelties, entertaining but impractical. Others recognized them as the beginning of something significant, though they could not predict the specific ways in which these vehicles would eventually reshape society. A few jurisdictions passed laws restricting or regulating mechanical vehicles, concerned about safety, noise, or the disruption of established traffic patterns. The machines themselves were too rare and too unreliable to pose any immediate challenge to horse-drawn transport. but they represented a different future whose outline was beginning to become visible. The problem of steering required solutions that were not obvious. Horses turned where the driver directed them, applying intelligence and muscle to the task of navigating around obstacles and following paths. A mechanical vehicle needed some method to change the direction of its wheels precisely and reliably, responding to the operator's intentions without delay or excessive force. Early systems used tillers similar to those on boats, requiring the driver to push or pull on a handle connected to the front wheels through various linkages. These tiller mechanisms demanded careful design. The forces involved in turning wheels that carried weight while the vehicle was moving were substantial, and operators needed enough mechanical advantage to overcome resistance without making the system so sensitive that small movements caused large directional changes. Engineers experimented with different ratios, different pivot points, different methods of connecting the steering mechanism to the wheels themselves. Some designs worked adequately at low speeds, but became difficult to control as velocity increased. Others steered smoothly, but required too much physical effort from the operator. The question of braking presented similar challenges. A vehicle moving at speeds that exceeded what horses could sustain needed reliable methods to slow and stop. Methods that worked consistently in different conditions and did not degrade too quickly with use. Friction brakes that pressed against wheels or rotating drums generated heat and wore down the materials in contact with each other. Designers had to select materials that could withstand repeated heating and cooling, that maintained their friction characteristics as they wore, that would not fail catastrophically under heavy use. Early brake systems were often inadequate for the speeds the vehicles could achieve, leading to situations where operators could not stop quickly enough to avoid collisions or hazards. This mismatch between power and control became a central concern. It did no good to build an engine capable of propelling a vehicle at impressive speeds if the machine could not be safely operated at those speeds. The balance between acceleration and deceleration, between power and control, required careful engineering of multiple systems working together. Suspension systems had to absorb the shocks and vibrations of roads that were designed for iron-rimmed wheels moving at walking pace, not for vehicles traveling at 2 or 3 times that speed. Springs made from steel could store and release energy as the vehicle encountered bumps and irregularities, smoothing the ride for passengers and reducing stress on the mechanical components. But springs needed to be calibrated to the weight of the vehicle and the characteristics of the roads it would travel. And getting this calibration right required testing under real conditions. The earliest suspension designs were crude, offering minimal isolation from the road surface. Passengers felt every bump and hole, and the constant jarring made long journeys exhausting and sometimes nauseating. Improvements came incrementally as engineers tested different spring rates, different mounting points, different combinations of rigid and flexible components. Each refinement made the vehicle slightly more comfortable, and slightly more durable, addressing the reality that comfort and reliability were connected. A system that transmitted every shock to passengers also transmitted those forces to bolts and welds that would eventually loosen or crack. Lighting presented another challenge that became more urgent as vehicles improved enough to be used in the evening or early morning. Candle lanterns and oil lamps provided dim, flickering illumination that barely penetrated darkness, making it difficult to see obstacles or navigate unfamiliar routes. Acetylene lamps produced brighter light by burning gas generated from calcium carbide and water, but they required careful maintenance and posed fire risks. Electrical lighting was cleaner and safer, but required batteries that added weight and needed regular charging. The complexity of these vehicles meant that operators needed mechanical knowledge and problem-solving ability. A breakdown miles from any workshop required the driver to diagnose and repair problems using whatever tools and materials were available. This necessity shaped the early culture around self-powered vehicles. It was a domain of enthusiasts and mechanics, people who enjoyed the challenge of keeping complex machines running, who took satisfaction in understanding how systems worked and why they sometimes failed. The vehicles were projects as much as they were transportation, demanding attention and skill from those who used them. The transition from experimental curiosity to practical tool required more than isolated breakthroughs. It demanded the slow accumulation of small improvements, each one addressing a specific limitation or failure mode that prevented reliable operation. Engineers collected data from every journey, noting which components failed most frequently, under what conditions problems emerged, how different materials performed over time. This empirical knowledge guided incremental refinements that gradually transformed temperamental machines into devices that could be operated with reasonable confidence. Metallurgy played a crucial role in this evolution. The stresses imposed by internal combustion engines, the repeated explosions, the high temperatures, the rapid vibrations, required materials that could withstand conditions more severe than most industrial applications demanded. Steel alloys needed sufficient strength to resist fracture while retaining enough flexibility to absorb shock without becoming brittle. Castings had to be uniform in composition and free from internal flaws that would propagate into cracks under cyclic loading. The science of metals advanced partly in response to the demands of vehicle construction, as manufacturers learned which compositions worked and which failed. Pistons moved within cylinders at speeds and temperatures that caused rapid wear if the clearances were not precisely controlled. Too tight, and friction would generate excessive heat, potentially seizing the engine. Too loose, and gases would escape past the piston, reducing power and efficiency. Machinists developed techniques to bore cylinders to exact dimensions, to finish surfaces smooth enough to minimize friction, to maintain tolerances measured in fractions of millimeters. This precision manufacturing represented a significant advance in industrial capability, spreading beyond vehicle production to other domains where tight tolerances mattered. The fuel itself evolved as demand created incentives for refinement. Early petroleum distillates were inconsistent in quality, varying in volatility and energy content, depending on the source and processing methods. Engines designed for one batch of fuel might run poorly or not at all on another batch. Standardization of fuel quality became necessary as vehicles proliferated, leading to the development of specifications and testing procedures that ensured minimum performance characteristics. The infrastructure for distributing this fuel began to emerge: storage tanks, delivery systems, retail locations where operators could repurchase supplies. Ignition systems required reliable methods to create sparks at precisely the right moment in each cylinder's cycle. Early systems used mechanical contacts that wore quickly, electrical components that were sensitive to moisture and vibration, and timing mechanisms that drifted out of adjustment. Improvements came through better insulation of wires, more durable contact materials, designs that isolated sensitive components from the harsh environment of the engine compartment. The reliability of ignition became one of the key factors determining whether a vehicle could start consistently and run smoothly. Cooling systems had to remove the heat generated by combustion without adding excessive weight or complexity. Air cooling used fins and airflow to dissipate heat, relying on the vehicle's motion to provide ventilation. Water cooling circulated liquid through channels in the engine block, carrying heat to a radiator where air could absorb it. Each approach had advantages and disadvantages. Air cooling was simpler, but less effective at high loads. Water cooling was more efficient, but added components that could leak or freeze. Engineers chose between these options based on the specific requirements of different vehicle designs. Transmissions allowed engines to operate in their most efficient range, while the vehicle traveled at different speeds. Gear sets with different ratios enabled high torque for starting and climbing hills, and lower mechanical advantage for sustained cruising. The challenge was creating smooth transitions between ratios, mechanisms that could shift under load without grinding or jamming, systems that would endure thousands of shifts without excessive wear. Early transmissions were often the weakest link in the drivetrain, requiring frequent maintenance and occasional rebuilding. The accumulation of these refinements happened across many workshops and factories, each contributing solutions to particular problems. Knowledge spread through technical publications, through workers who moved between companies, through the analysis of competing products. No single inventor or manufacturer created the complete vehicle. It emerged from a distributed process of improvement, where each participant built on what others had discovered, adding their own insights and innovations to an expanding body of practical knowledge. Tires represented a critical interface between vehicle and road, and their evolution dramatically affected performance and comfort. Solid rubber tires provided durability, but transmitted every irregularity directly to the vehicle frame. Pneumatic tires filled with air offered cushioning that absorbed shocks, but they were vulnerable to punctures and required regular maintenance to maintain proper pressure. The rubber itself needed to resist abrasion from road surfaces while remaining flexible enough to deform and recover thousands of times per mile. Early pneumatic tires failed frequently, sometimes multiple times on a single journey. Operators carried patches, spare inner tubes, pumps, and the tools needed to remove wheels and make repairs. A puncture could add an hour to a trip, and the constant risk of tire failure made long journeys uncertain. Improvements in rubber compounds, in tire construction, and in the design of wheels and rims gradually reduced the frequency of failures, though flat tires remained a common occurrence for decades. The electrical system expanded from a simple ignition circuit to include lighting, starting motors, and instruments. Batteries capable of storing sufficient energy for these functions without excessive weight or size required advances in electrochemistry. Lead-acid batteries proved most practical, using chemical reactions between lead plates and sulfuric acid to store and release electrical energy. These batteries needed protection from vibration, required periodic addition of water, and gradually lost capacity over their lifetime, but they provided reliable power when properly maintained. Starting mechanisms evolved from hand cranks that required strength and technique to electrical starters that allowed anyone to start an engine with the turn of a key. The hand crank was dangerous. If the engine backfired during cranking, the handle could reverse violently, breaking arms or wrists. Electric starters eliminated this hazard while making vehicles accessible to people who lacked the physical capability to crank start an engine. This seemingly simple change had profound effects on who could operate vehicles and therefore on how vehicles integrated into daily life. Instrumentation gave operators information about the vehicle's condition, speed, engine temperature, oil pressure, fuel level. Early vehicles had minimal instrumentation, requiring operators to judge everything by sound, vibration, and external observation. As systems became more complex and speeds increased, the need for quantitative information became apparent. Gauges used mechanical linkages or electrical sensors to translate physical conditions into visual displays that operators could monitor while driving. The layout of controls gradually standardized as manufacturers discovered arrangements that minimized the operator's workload and reduced errors. Pedals for clutch, brake, and throttle settled into positions that became familiar across different brands and models. Steering wheels replaced tillers, providing better leverage and a more intuitive connection between the operator's movement and the vehicle's response. The dashboard organized instruments and switches in locations that could be seen and reached without taking attention from the road for more than a brief glance. Manufacturing techniques advanced to meet the demand for vehicles as they transitioned from hand-built machines to factory products. Interchangeable parts required precision in machining and standardization of dimensions so that components from different production batches would fit together without custom fitting. Assembly processes were organized to move vehicles through sequential stations where specific tasks were performed, reducing the time and skill required to complete each unit. This industrial approach lowered costs and increased production volume, making vehicles accessible to a broader population. Materials beyond metal entered the design: glass for windows, leather and fabric for interior surfaces, wood for structural elements and decorative details. Each material had to withstand conditions specific to vehicle use: temperature extremes, vibration, exposure to oil and fuel, the wear of constant human contact. Suppliers developed specialized products for these applications, creating an ecosystem of component manufacturers whose expertise in specific materials and processes supported the vehicle industry. The accumulation of all these improvements happened gradually enough that no single change marked a clear before and after, yet collectively they transformed what vehicles could do and who could use them. The machines became more reliable, more comfortable, more powerful, and easier to operate. This progression was not smooth or inevitable. There were dead ends, failed approaches, designs that worked in theory, but not in practice. But the general direction was toward increased practicality. And as practicality increased, so did adoption. The heart of the vehicle was a system that converted the potential energy stored in fuel into the kinetic energy of motion through a series of precisely timed events that repeated thousands of times per minute. Inside each cylinder, a mixture of air and vaporized fuel entered through an opening controlled by a valve, was compressed by the upward movement of a piston, ignited by a spark that arrived at exactly the right moment, and expanded explosively to drive the piston downward. The exhaust gases exited through another valve, and the cycle began again, over and over, with a regularity that depended on the accuracy of dozens of moving parts working in coordination. The crankshaft transformed the linear motion of pistons into rotational motion that could be transmitted to wheels. This component experienced forces from multiple directions as pistons pushed down at different points in their cycles, creating a complex pattern of stress that varied constantly. The shaft needed to be balanced so it would rotate smoothly without vibration, machined to tolerances that ensured bearings would not wear prematurely, and strong enough to transmit full engine power without flexing or twisting. The quality of the crankshaft often determined how long an engine would run before requiring major service. Bearings supported rotating shafts while allowing them to spin freely, and their design represented a balance between reducing friction and providing adequate support. Plain bearings use smooth surfaces separated by a thin film of oil, relying on fluid dynamics to prevent metal-to-metal contact. Ball or roller bearings used hardened steel elements that rolled between races, distributing load across multiple contact points. Each type had applications where it excelled, and engineers selected bearing designs based on the specific forces and speeds each location in the drivetrain would experience. Lubrication was not a detail, but a fundamental requirement that prevented the entire system from destroying itself through friction. Oil circulated through passages drilled in the engine block, reaching bearings, cylinder walls, valve mechanisms, and gear teeth. The oil film prevented direct contact between moving metal surfaces, absorbed heat generated by friction, and carried away particles of wear debris that accumulated during operation. The oil itself degraded over time as heat broke down its molecular structure and contamination reduced its effectiveness, requiring periodic replacement to maintain protection. Valve trains controlled the opening and closing of intake and exhaust valves, with timing synchronized to the crankshaft's rotation. Camshafts, with precisely shaped lobes, pushed on followers or rocker arms that opened valves against spring pressure, holding them open for exactly the duration needed for gases to flow in or out, then allowing springs to snap them shut before the next cycle began. The geometry of these components determined how aggressively valves opened, how long they stayed open, and how quickly they closed. Parameters that affected power output, efficiency, and the character of the engine's performance. The combustion chamber's shape influenced how the fuel-air mixture burned, affecting efficiency and the tendency for premature ignition that could damage pistons and valves. Engineers experimented with different chamber geometries, learning how turbulence patterns affected flame propagation, how compression ratios influenced power and efficiency, how combustion characteristics changed with different fuels. This knowledge accumulated through testing and analysis, gradually improving the extraction of energy from each drop of fuel. Cooling passages cast into the engine block carried water heated by combustion to a radiator where airflow removed the thermal energy. Thermostats regulated coolant flow to maintain optimal operating temperature, warm enough for efficient combustion and proper oil viscosity, but cool enough to prevent damage to gaskets and metal components. The balance was delicate, and cooling system failures could destroy an engine in minutes if not detected and addressed quickly. Exhaust systems channeled hot gases away from the engine, reducing noise while allowing gases to exit with minimal back pressure that would impede the next cycle's exhaust stroke. The design of exhaust manifolds, pipes, and mufflers affected engine performance in subtle but measurable ways, and engineers learned to tune these components to optimize power delivery at specific engine speeds. The components themselves had to withstand high temperatures and corrosive exhaust gases without cracking or rusting through. The fuel delivery system metered the precise quantity of liquid fuel needed for each combustion event, atomized it into fine droplets that would mix with air and vaporize, and delivered this mixture to cylinders in proportions that varied with engine load and speed. Carburetors accomplished this through ingenious arrangements of passages, jets, floats, and venturies that used airflow and vacuum to draw and mix fuel without electrical or mechanical power. The tuning of these devices required understanding of fluid dynamics and extensive calibration to achieve smooth operation across the range of conditions an engine would encounter. The throttle controlled power output by regulating how much air-fuel mixture entered the engine. Opening the throttle allowed more mixture to flow, increasing power. Closing it restricted flow, reducing power. This seemingly simple function required careful design to provide smooth, predictable response to the operator's input. Linkages connected the throttle pedal or lever to the carburetor, translating foot pressure into precise movement of a valve or butterfly plate. Any slack or friction in this linkage degraded the operator's ability to control the vehicle smoothly. The clutch connected and disconnected the engine from the transmission, allowing the engine to run while the vehicle was stationary and enabling smooth engagement of power when starting from a stop. Friction surfaces, pressed together by spring force, transmitted torque when engaged, and separation of these surfaces broke the connection when the clutch pedal was depressed. The friction materials had to withstand high temperatures generated during engagement, resist wear from the constant cycling of connection and disconnection, and provide consistent behavior throughout their service life. The transmission contained multiple gear sets that could be selectively engaged to provide different ratios between engine speed and wheel speed. Lower gears provided high mechanical advantage for starting and climbing hills, sacrificing maximum speed for increased torque at the wheels. Higher gears reduced mechanical advantage, allowing higher speeds with the engine running at sustainable revolutions per minute. Shifting between gears required synchronizing the speeds of different components, and mechanisms called synchronizers used friction to match these speeds before gear teeth engaged, preventing grinding and allowing smooth shifts. The driveshaft carried rotational power from the transmission to the differential, a device that allowed wheels on the same axle to rotate at different speeds when the vehicle turned. Without this capability, one wheel would need to slip during turns, causing excessive tire wear and making steering difficult. The differential used a clever arrangement of gears to split input torque between two output shafts while allowing speed differences between them, solving a fundamental problem in vehicle dynamics. Axles transmitted power from the differential to the wheels while supporting the vehicle's weight and maintaining wheel alignment. The loads on axles were complex: vertical forces from weight and road irregularities, horizontal forces from acceleration and braking, twisting forces from torque transmission. The axle housing had to be rigid enough to maintain precise wheel positioning, while strong enough to resist the various loads without bending or breaking. Bearings at the wheel hubs allowed wheels to spin freely while supporting radial and thrust loads. Suspension components isolated the vehicle body from road irregularities, maintaining tire contact with the road surface while allowing vertical movement to absorb bumps and holes. Springs stored energy as they compressed and released it as they extended, supporting weight while permitting motion. Dampers dissipated energy to prevent springs from bouncing repeatedly after encountering a disturbance, using fluid forced through small orifices to convert kinetic energy into heat. The interaction between springs and dampers determined ride quality and handling characteristics. Steering linkages connected the steering wheel to the front wheels through a series of rods, joints, and levers that converted the rotating motion of the wheel into the angular movement of the wheels. The geometry of these linkages had to maintain proper wheel alignment through the full range of steering motion, prevent excessive play that would make steering imprecise, and provide feedback to the operator about what the wheels were experiencing. Ball joints and tie rod ends allowed movement while maintaining connection, using grease-filled housings to protect the bearing surfaces from contamination. Brakes converted the vehicle's kinetic energy into heat through friction, slowing or stopping the motion. Brake shoes or pads pressed against drums or discs attached to the wheels, using the friction between dissimilar materials to resist rotation. The force applied to the brake pedal was multiplied through mechanical or hydraulic linkages to generate sufficient clamping force at each wheel. The heat generated during heavy braking could cause brake components to fade, losing effectiveness as temperatures climbed beyond the material's designed operating range, requiring operators to anticipate stops and avoid excessive heating of the brake system. The proliferation of different designs created a landscape of incompatibility that hindered the practical use of vehicles across different regions and manufacturers. A part that failed on one brand could not be replaced with a component from another, forcing operators to either carry extensive inventories of spares or risk being stranded when something broke. This fragmentation meant that knowledge gained maintaining one type of vehicle did not necessarily transfer to another, and mechanics who could service one brand might be unable to repair a different, even when the underlying principles were identical. The pressure towards standardization came from multiple directions. Manufacturers recognized the common dimensions for bolts, fittings, and mounting points would simplify production and reduce the number of unique tools required for assembly and service. Operators wanted the assurance that parts would be available wherever they traveled, not just in the city where the vehicle was purchased. Mechanics needed access to replacement components without maintaining separate inventory for every brand they might encounter. These practical considerations gradually overcame the initial impulse toward proprietary designs. Thread standards for bolts and nuts emerged as one of the earliest areas of agreement. Different thread pitches and profiles had proliferated as each manufacturer made their own choices. But this variety meant that wrenches and bolts from one vehicle would not fit another. Industry groups proposed standard thread forms and pitches for different bolt sizes, and manufacturers slowly adopted these specifications. The transition was not instantaneous. Older vehicles retained their unique threads, while newer production incorporated the standards. But over time, the common specifications became dominant. Electrical systems converged on standard voltages as the advantages of compatibility became apparent. Batteries, generators, light bulbs, and accessories designed for one voltage could not be used with systems operating at different voltages, and this incompatibility increased costs and complexity. Agreement on voltage standards meant that electrical components became interchangeable across brands, creating a larger market for suppliers and reducing prices through economies of scale. The standardization extended to connector designs, wire gauges, and circuit protection devices. Fuel quality standards protected both operators and manufacturers from the problems caused by inconsistent petroleum products. Engines designed for fuel with specific characteristics would perform poorly or suffer damage when supplied with fuel of different composition. Specifications for volatility, octane rating, and contamination limits ensured that fuel purchased anywhere would meet minimum requirements for safe operation. Testing procedures verified compliance with these standards, and regulatory oversight enforced them, creating confidence that the fuel would be suitable for the vehicle. Tire sizes standardized around rim diameters and tire widths, allowing operators to replace worn tires with products from different manufacturers that would fit the same wheels. The designation systems indicated the dimensions in ways that were consistent across brands, though different systems existed in different regions, and the process of global harmonization took decades. The standardization of tire mounting interfaces meant that the same equipment could service different vehicles, reducing the investment required for tire shops and service stations. Lighting standards specified the brightness, color, and placement of headlamps, taillights, and signal indicators. These standards served safety purposes by ensuring that vehicles were visible to others and that lighting patterns had consistent meanings. Red lights indicated the rear of a vehicle. Turn signals blinked at prescribed rates. Brake lights illuminated when the vehicle was slowing. The standardization of mounting points and electrical connections for lights simplified replacement and repair, allowing aftermarket suppliers to produce compatible components. The dimensional standards for fuel tank openings, oil fill caps, and other service points enabled the development of compatible equipment at service stations. Fuel nozzles that fit one vehicle would fit others, allowing standardized dispensing equipment. Oil and fluid containers could be designed with spouts that fit standard openings. These seemingly minor compatibility issues had significant practical impact. Without standardization, servicing vehicles would require custom tools and fittings for each brand, making roadside assistance and commercial fueling infrastructure far more complex. Manufacturing processes standardized around methods that proved most efficient and reliable, creating consistency in quality and capability across the industry. The techniques for casting engine blocks, machining cylinder bores, and heat-treating components became similar across different manufacturers as best practices emerged from collective experience. Workers trained at one factory could transfer their skills to another because the equipment and procedures were fundamentally similar, even if the specific products differed in detail. Assembly line production standardized not just the vehicles themselves, but the process of building them, the sequential organization of tasks, the specialization of workers on specific operations, the flow of materials to workstations, These methods spread through the industry because they demonstrably reduced production time and cost. The standardization of assembly methods meant that improvements developed at one facility could be adapted by others, creating a rising baseline of manufacturing efficiency that benefited the entire industry. Quality control procedures standardized around inspection methods and acceptance criteria that verified components met specifications before assembly. Gauges and fixtures checked dimensions at multiple stages of production, catching deviations early before they became incorporated into finished vehicles. Standardized testing procedures for completed vehicles verified that brakes, steering, lights, and other systems functioned correctly before delivery. These quality practices reduced the variation between individual vehicles, improving reliability and customer satisfaction. Training programs standardized the knowledge required to operate and maintain vehicles, creating curricula that covered the fundamental principles and common procedures applicable across different brands. Technical schools taught the theory of internal combustion engines, electrical systems, and mechanical power transmission in ways that applied broadly rather than focusing on proprietary designs. This standardized education meant that mechanics could understand and service unfamiliar vehicles by applying general principles, even when specific details differed. Service manuals adopted similar formats and organizational structures, making technical information easier to find and use. Exploded diagrams showed how parts fit together. Specifications listed critical dimensions and tolerances. Procedures described the sequence of steps for maintenance and repair. The standardization of technical documentation reduced the learning curve when working on unfamiliar vehicles and improved the accuracy of service work by providing clear, consistent information. Traffic regulations standardized the rules governing vehicle operation, creating predictable patterns of behavior that improved safety and efficiency. Rules about which side of the road to use, who had priority at intersections, how to signal intentions, and where stopping was permitted varied by jurisdiction, but within each jurisdiction applied equally to all vehicles. The standardization of these rules made it possible to operate a vehicle in unfamiliar areas by following the same conventions that applied elsewhere, reducing confusion and accidents. Road signs standardized visual communication between infrastructure and operators, using shapes, colors, and symbols with consistent meanings. A stop sign looked the same everywhere it was used. A warning sign used recognizable geometry and color coding. Directional signs followed format conventions that made them quickly interpretable. This standardization was particularly important as vehicles enabled people to travel into unfamiliar territories where local knowledge could not be assumed. Licensing and registration systems standardized the documentation of vehicle ownership and operator qualifications, creating records that could be verified across jurisdictions. License plates identified vehicles uniquely. Operator licenses certified that individuals had demonstrated basic competence. Registration documents established legal ownership and tax compliance. These administrative standards supported enforcement of regulations and resolution of disputes about responsibility when accidents or violations occurred. The accumulation of standards created an infrastructure of compatibility that transformed vehicles from isolated machines into elements of a coherent system. A vehicle manufactured in one location could be fueled, serviced, and operated anywhere the system extended, using parts and expertise that were available because standardization made them economically viable. This compatibility was not complete. Variations and proprietary elements persisted, but the trend towards standardization was powerful because it served the interests of manufacturers, operators, and service providers simultaneously. The invisible work of committees, industry groups, and regulatory bodies in establishing these standards enabled the practical expansion of vehicle use in ways that would have been impossible in a completely fragmented landscape. The displacement of horses happened gradually enough that many people did not recognize it as a fundamental shift until it was already well advanced. In the early years, vehicles and horses shared the same streets, operating according to different logics, but coexisting in an uneasy mixture. The horses moved at their ancient pace, responding to the voices and reins of drivers who had learned their trade over years of working with animals. The vehicles moved with mechanical insistence, their operators focused on controls and gauges rather than on the living responsiveness of a team. The economics favored machines in ways that became more pronounced as reliability improved and costs decreased. A horse required daily care whether it worked or not. Feeding, watering, grooming, hoof maintenance, veterinary attention when illness or injury occurred. The animal needed rest periods and could only work so many hours before exhaustion compromised its health. A vehicle sat idle without consuming resources, started when needed, and operated as long as fuel remained in the tank, limited by mechanical endurance rather than biological fatigue. For commercial operators, this difference in operating costs accumulated into significant advantages. A delivery business using vehicles could cover more territory with fewer assets, making more trips in the same amount of time, carrying loads that would require multiple horses and wagons. The speed of delivery improved, allowing businesses to promise faster service and respond to urgent requests in ways that animal transport made difficult. These competitive pressures encouraged adoption even among those who preferred working with horses or who had invested substantially in animal-based infrastructure. The infrastructure that had supported horse transport began to disappear as demand shifted. Stables that had housed working animals closed or converted to other uses. Blacksmiths who had specialized in horseshoeing found their trade declining and adapted by learning to work on vehicles or left the profession entirely. Feed suppliers, harness makers, carriage builders, all the trades that had grown around animal transport faced contraction as their services became less necessary. The transition was not catastrophic for most because it happened over years, allowing gradual adjustment, but it represented a restructuring of urban economies. The streets themselves changed character as the proportion of vehicle traffic increased. The sound environment shifted from the clop of hooves and jangle of harnesses to the rumble of engines and the squeal of brakes. The smell changed from manure and animal sweat to exhaust and hot oil. The pace of traffic accelerated as vehicles established the rhythm and horses became obstacles that slowed the flow. Traffic rules evolved to accommodate the different capabilities and limitations of mechanical transport, creating expectations about speed and right-of-way that increasingly favored vehicles. Public transportation systems faced a choice between continuing to rely on streetcars pulled by horses or converting to mechanical or electrical power. The operating economics clearly favored powered vehicles. They were faster, more reliable, required less maintenance infrastructure, and could operate longer routes without the need for animal replacement at intermediate points. Cities invested in electrified streetcar systems or motorbus routes, retiring the horse-drawn vehicles that had provided mass transit for decades. The transition improved service while eliminating thousands of jobs for drivers, stable workers, and animal caretakers. Personal transportation shifted more slowly because the initial cost of a vehicle was substantial and because many people lacked the mechanical knowledge to maintain them. Families that kept a horse for personal use made do with existing arrangements until the vehicle became affordable and practical enough to justify the transition. But as used vehicles became available, and as operating costs fell, the advantages of mechanical transport became accessible to a broader population. The flexibility of being able to travel on impulse without the need to harness and prepare an animal appealed to those whose time was valuable. Rural areas retained horse transport longer than cities because the economics were different. Farms needed animals for work beyond transportation, plowing, hauling, powering equipment. The infrastructure for supporting vehicles was less developed in rural regions, with longer distances between fuel supplies and repair facilities. Roads were often unpaved and challenging for early vehicles. But even in rural areas, the trend was clear. Tractors replaced draft horses for field work, trucks replaced wagons for hauling crops to market, and personal vehicles replaced buggies for trips to town. The knowledge required to work with vehicles gradually replaced the knowledge of working with animals as an essential skill for anyone involved in transportation. The understanding of horse behavior, of how to read an animal's condition and mood, of the techniques for harnessing and driving. This accumulated wisdom that had been passed down through generations became less relevant with each passing year. In its place came the knowledge of mechanical systems, of how to diagnose engine problems by sound, of the procedures for maintenance and minor repairs that kept vehicles operating reliably. Educational institutions adapted by introducing technical training programs that taught the principles of vehicle operation and repair. These programs drew students who saw opportunity in the expanding vehicle industry, people who might previously have apprenticed as teamsters or stable workers. The curriculum covered topics that had no equivalent in animal transport: electrical circuits, fuel systems, metallurgy, precision measurement. The shift represented not just a change in what was taught, but a different kind of knowledge, more technical and less dependent on the intuitive understanding that came from working with living things. The generation that had grown up with horses found themselves navigating a world increasingly organized around vehicles, and the adaptation varied by individual circumstance. Some embraced the new technology enthusiastically, appreciating the speed and convenience it offered. Others maintained their preference for horses as long as practical, skeptical of the reliability of machines or attached to the familiar rhythms of animal transport. But practical necessity often overcame preference. When the infrastructure for supporting horses diminished, when the time costs of slower travel became too burdensome, when social expectations shifted toward vehicle ownership, the transition became difficult to resist. Children growing up in this transitional period often had experience with both modes of transport, learning to drive vehicles while still knowing how to harness a horse. But their children, born into a world where vehicles were common, often never developed the skills their grandparents had considered essential. The knowledge of animal transport faded not through conscious abandonment, but through simple irrelevance. There was no reason to learn something that had no application in daily life. The living connection to the modes of transportation that had served humanity for millennia broke within the span of a single generation. Urban planning began to reflect the dominance of vehicles in ways that would have been unthinkable a few decades earlier. Streets were widened to accommodate higher traffic volumes and faster speeds. Parking areas appeared where stables had once stood. Traffic signals replaced policemen at busy intersections, using electrical timing to manage flow more efficiently than human judgment could. The geometry of cities started to change, spreading outward as vehicle ownership made longer commutes feasible, reducing the density that had been necessary when most people walked or used mass transit. The environmental impact of this transition was complex and not fully understood at the time. The elimination of horse populations from cities removed a significant source of waste and associated health problems. The manure, the flies, the contamination of water supplies. Streets became cleaner in this specific way, though the exhaust from thousands of vehicles introduced different forms of pollution that would eventually be recognized as problematic. The immediate perception was that vehicles were cleaner than horses, and this perception reinforced the sense that the transition represented progress. The speed at which this transition occurred varied by region and economic development. Wealthier urban areas made the shift quickly, with vehicles becoming dominant within a couple of decades. Less developed regions took longer, maintaining mixed systems where horses and vehicles coexisted for extended periods. But the direction was universal. Once the infrastructure for supporting vehicles reached a certain density, network effects accelerated adoption. Service stations, repair facilities, paved roads, traffic management systems. Each element of infrastructure made vehicles more practical, which increased their numbers, which justified further infrastructure investment. The cultural meaning of horses shifted as their practical role diminished. What had been working animals, valued for strength and endurance and temperament, became recreational or symbolic. Horses persisted in rural work longer than in cities, retained roles in certain traditional activities, and developed new purposes in sport and leisure. But the everyday intimacy between humans and horses, the relationship that had existed for thousands of years across most of human civilization, largely ended within a few decades. The vehicle replaced not just a mode of transport, but a form of relationship, though few at the time articulated the loss in those terms, focused as they were on the gains in speed and efficiency. The expansion of vehicle use demanded physical modifications to the landscape on a scale that reshaped entire regions. Roads that had served adequately for horse-drawn traffic, packed earth, gravel surfaces, narrow widths designed for vehicles moving at walking pace, became inadequate for the speeds and volumes of mechanical transport. The wheels of vehicles churned soft surfaces into mud during rain, creating ruts that made travel difficult and damaged the vehicles themselves. Dust rose in clouds during dry weather, coating everything nearby and reducing visibility. The need for improved road surfaces became urgent as vehicle numbers increased. Paving with hard surfaces provided the solution, but required enormous investment in materials and labor. Concrete and asphalt created durable surfaces that resisted weather, supported heavy loads without deforming, and provided smooth travel that reduced wear on vehicles and improved comfort for passengers. The construction process involved preparing the roadbed by grading and compacting soil, laying foundation layers of crushed stone, and applying the final paving material in thicknesses calculated to support expected loads. Miles of road required thousands of tons of material transported to work sites, mixed or laid with specialized equipment, and finished to specifications that ensured proper drainage and durability. The width of roads increased to accommodate multiple lanes of traffic moving in opposite directions, with additional space for vehicles to pass slower-moving traffic safely. Curves were redesigned with gentler radii that could be navigated at higher speeds without requiring vehicles to slow dramatically. Grades were reduced where possible to minimize the load on engines climbing hills and the stress on brakes descending them. Intersections were configured to allow traffic to merge and cross with reduced conflict, using geometric layouts that considered the turning radius of vehicles and the side distances needed for safe decisions. Bridges required complete redesign to support the concentrated loads of heavy vehicles rather than the distributed weight of horse-drawn wagons. The engineering calculations accounted for dynamic forces generated when vehicles crossed at speed, for the repetitive loading that would occur thousands of times daily, for the environmental stresses of temperature changes and weather exposure. Steel and reinforced concrete became the primary materials, replacing timber and stone structures that lacked the strength and durability needed for intensive vehicle use. The construction of a single major bridge could take years and consume budgets that would have built dozens of miles of basic road. Signage systems emerged to guide drivers through increasingly complex road networks. Direction signs indicated routes to distant cities, allowing travelers to navigate without local knowledge. Warning signs alerted drivers to upcoming hazards, sharp curves, steep grades, narrow passages, railway crossings. Regulatory signs communicated speed limits, parking restrictions, and other rules. The design of these signs standardized around shapes and colors that could be recognized and understood quickly at the speeds vehicles traveled, creating a visual language that extended across entire nations and eventually across borders. Traffic control devices managed the flow of vehicles at intersections and along congested routes. Traffic lights used colored signals with universally understood meanings: red for stop, green for go, yellow for caution. The timing of these signals could be adjusted to favor the heavier traffic flows, reducing wait times and improving overall throughput. In some locations, the lights were coordinated along corridors so that vehicles maintaining a certain speed would encounter a sequence of green lights, creating waves of continuous movement. The electrical infrastructure to power and control these devices required underground cables, control boxes, and maintenance systems. Fuel distribution networks spread across populated areas, placing service stations within convenient distance of major routes and population centers. These facilities needed underground tanks to store fuel safely, pumps to dispense it efficiently, and retail space where operators could purchase supplies and minor accessories. The placement of service stations followed the logic of vehicle range and traffic patterns, creating corridors of frequent stations along busy routes and sparser coverage in less traveled areas. The capital investment in this infrastructure was substantial, justified by the ongoing revenue from fuel sales to the growing vehicle fleet. Repair facilities appeared wherever vehicle density justified them, offering services from minor maintenance to major overhauls. These shops needed specialized tools and equipment: lifts to raise vehicles for access to undercarriages, diagnostic instruments to identify problems, parts inventory to support common repairs. The skilled labor required to staff these facilities commanded wages that reflected the technical knowledge needed, and the shortage of qualified mechanics in the early years of rapid expansion created opportunities for those willing to learn the trade. The geographic distribution of repair facilities determined how far people could travel from home with confidence that help would be available if something failed. Parking facilities transformed urban landscapes as vehicle ownership expanded beyond the capacity of street-side spaces. Multi-level structures appeared in dense areas, using steel and concrete to stack parking spaces vertically where horizontal space was too valuable or scarce for surface lots. The design of these structures had to accommodate the minimum dimensions needed for vehicles to maneuver. With ramps connecting levels at grades, vehicles could climb and descend safely. Lighting, ventilation, and fire safety systems were necessary to make these enclosed spaces functional and safe for both vehicles and the people using them. The legal framework for road use evolved to address the unique characteristics and risks of mechanical transport. Speed limits restricted how fast vehicles could travel on different types of roads, balancing the desire for rapid travel against safety considerations and road design limitations. Registration requirements created records of vehicle ownership for taxation and liability purposes. Operator licensing systems verified that drivers possessed minimum competency before allowing them to use public roads. Insurance requirements shifted financial responsibility for accidents to a system that could compensate victims without requiring individual drivers to possess sufficient personal wealth to cover potential damages. Traffic enforcement developed methods and technologies to detect violations and identify violators. Police departments created specialized units that patrolled roads, observed traffic patterns, and stopped vehicles suspected of violating regulations. The enforcement of speed limits required methods to measure vehicle velocity accurately, initially through pacing by police vehicles, later through timing devices, and eventually radar systems. The documentation of violations, the processing of citations, and the adjudication of disputes created administrative systems that paralleled the courts handling other legal matters. Highway systems connected cities and regions with roads designed specifically for long-distance vehicle travel at sustained high speeds. These routes bypassed town centers, used controlled access to minimize conflicts with crossing traffic, and maintained higher construction standards than local roads. The planning of highway networks considered economic development, military mobility, and the connection of population centers in ways that would maximize utility and justify the enormous construction costs. The routes chosen often determined which communities would thrive with easy access to regional commerce and which would remain relatively isolated. Rest areas along highways provided facilities for operators to stop safely when fatigue or biological needs required breaks from continuous travel. These areas included parking, restrooms, and sometimes fuel and food services, creating oases of amenity along routes that might otherwise require traveling for hours without services. The spacing of rest areas reflected typical travel ranges and driver endurance, with denser placement along heavily traveled routes and sparser coverage on less busy highways. Maintenance systems kept the road infrastructure functional despite constant use and environmental degradation. Crews repaired potholes formed when water infiltrated pavement and froze, patched cracks before they expanded into larger failures, repainted lane markings worn away by traffic, and replaced damaged signs. Winter maintenance in cold climates required plowing snow and applying salt or sand to improve traction, operations that had to be completed quickly to keep roads passable during storms. The ongoing cost of this maintenance was substantial, funded through fuel taxes, registration fees, and general revenues that channeled money from road users and the general public into the infrastructure that enabled vehicle transportation. Tunnel construction allowed roads to pass through obstacles that would otherwise require lengthy detours or prohibitively steep grades. The engineering challenges of tunneling included supporting the earth above the excavation, managing water infiltration, providing ventilation to remove vehicle exhaust, and creating emergency exits and fire suppression systems. The cost per mile of tunnel exceeded the cost of surface road by orders of magnitude, but in mountainous terrain or when passing under bodies of water, tunnels enabled connections that would otherwise have been impractical. Railway crossings created conflict points where two transportation systems intersected, requiring careful design to minimize accidents. Grade crossings at surface level used gates, lights, and warning bells to alert vehicle operators when trains approached. But these crossings remained dangerous locations where collisions occurred with tragic regularity. Grade separation, passing roads over or under railway lines, eliminated the conflict, but required significant construction of bridges or underpasses. The decision of which approach to use at each crossing balanced cost against traffic volumes and safety considerations. The cumulative effect of this infrastructure development was the creation of an environment where vehicles could operate efficiently across vast distances, where operators could travel with confidence that they would find fuel, services, and navigable routes, where the physical landscape had been modified to serve the needs of mechanical transport. This infrastructure represented an investment that exceeded the cost of the vehicles themselves many times over, a commitment by societies to a particular mode of mobility that would shape patterns of settlement, commerce, and daily life for generations. The vehicle enabled a compression of distance that altered fundamental relationships between communities and regions. Places that had been days apart by horse became hours apart by vehicle, and this reduction in travel time created economic connections that had been impractical under the constraints of slower transport. A farmer could deliver produce to a city market and return home the same day, expanding the radius of commercial agriculture beyond the immediate vicinity of urban centers. A merchant could visit multiple customers scattered across a region in the time it would have taken to reach a single distant location by horse. This compression of geography was not uniform. It followed the roads and concentrated along corridors where infrastructure investment had been heaviest. Regions connected by good roads experienced a tightening of economic and social bonds, while areas lacking paved routes remained relatively isolated, even as the broader world accelerated around them. The pattern of road development therefore became a determinant of which communities would participate fully in the emerging vehicle-dependent economy and which would find themselves increasingly peripheral. The movement of goods by a vehicle transformed supply chains and inventory management. Manufacturers could source materials from more distant suppliers if vehicle transport made timely delivery reliable. Retailers could reduce inventory because replenishment from regional warehouses could happen more frequently. Perishable goods could reach markets farther from their point of origin because travel time decreased below the threshold of spoilage. These changes rippled through economic systems, altering the logic of where production facilities located and how distribution networks organized themselves. The flexibility of vehicle transport compared to rail created new patterns of industrial geography. Factories were no longer constrained to locate near railway sidings. They could build wherever land costs and labor availability were favorable, relying on vehicle transport to connect them to suppliers and markets. This flexibility encouraged industrial dispersal, with manufacturing facilities appearing in smaller towns and rural areas that lacked rail service but had road access. The economic development that followed often altered the character of these communities, introducing industrial employment where agriculture had previously dominated. Tourism emerged as a significant economic activity enabled by vehicle mobility. People could visit scenic areas, historical sites, and recreational destinations that would have been difficult to reach by rail or horse. The journey itself became part of the experience, with the freedom to stop at points of interest along the way and the flexibility to explore without adhering to fixed schedules or predetermined routes. Businesses developed to serve this mobile population. Roadside accommodations, restaurants, fuel stations, souvenir shops, creating economic activity along routes that connected destinations. The geography of retail began to shift as merchants recognized that customers with vehicles could travel farther to shop, making location less dependent on proximity to concentrated populations. Stores could locate where land was cheaper and parking more abundant, attracting customers from wider areas by offering selection or prices that compensated for the travel required. Shopping districts that had developed around streetcar stops or railway stations found themselves competing with dispersed commercial development along highway corridors where vehicle access was easier and more convenient. Professional services expanded their geographic reach as practitioners could visit clients across larger territories. Doctors made house calls over wider areas. Lawyers served clients in multiple towns. Salespeople covered territories that would have been impossible to service efficiently with slower transportation. This expansion often meant that smaller communities that could not support full-time professionals of every type could still access services periodically, while larger centers saw their professionals serve hinterlands that extended well beyond the immediate vicinity. The social geography of families and friendships adapted to the increased mobility. People maintained relationships across greater distances when vehicle travel made periodic visits practical. Family gatherings drew participants from broader areas, and the definition of local community expanded to include people scattered across regions but connected by regular vehicle travel. The opposite also occurred. As mobility increased, the necessity of maintaining close relationships with immediate neighbors decreased, and some traditional forms of community obligation weakened. Migration patterns changed as vehicles made it practical to move belongings and families across distances that would have been prohibitively difficult with animal transport. People seeking employment could relocate to regions where opportunities existed, carrying household goods in vehicles or hiring transport services that used trucks instead of freight wagons. The reduced cost and complexity of moving encouraged geographic mobility. allowing labor markets to adjust more quickly to regional variations in demand and making it more feasible for people to pursue opportunities far from their place of birth. Emergency services achieved greater effectiveness through the speed of vehicle transport. Ambulances could reach accident or illness victims more quickly and transport them to medical facilities in time to receive treatments that would have been impossible if delayed by slower travel. Fire departments could respond to alarms across larger territories, arriving while fires were still controllable rather than after they had spread beyond hope of suppression. Police could cover wider areas and respond to incidents more rapidly, changing both the reality of law enforcement and the perception of public safety. Mail delivery frequencies increased as vehicles made it practical to move correspondence more often than daily rail service allowed. Multiple deliveries per day became possible in some urban areas, and remote locations that had received mail weekly could receive it several times per week. This acceleration of communication strengthened the connections between dispersed populations and reduced the isolation that distance had imposed when information traveled at the speed of horse-drawn mail wagons. The dispersion of education became possible as vehicles allowed students to travel from wider areas to consolidated schools that could offer better facilities and more specialized instruction than small local schools could provide. School districts reorganized around the assumption of vehicle transport, closing small rural schools and building larger regional facilities that served populations previously divided among many scattered one-room buildings. This consolidation had educational benefits, but also social costs, as very young children spend significant time in transit, and as schools became less integrated into the immediate life of small communities. Medical care centralized in similar ways, with small local practices and hospitals unable to compete with larger regional facilities that could afford specialized equipment and attract more qualified staff. Patients traveled greater distances for treatment, accepting the inconvenience because vehicle transport made the journey manageable and because the quality of care at larger facilities justified the effort. Rural areas that had maintained local doctors and small hospitals saw these services close or reduce scope as patient populations shifted to regional centers accessible by vehicle. Cultural exchanges accelerated as performers, speakers, and artists could tour more extensively, reaching audiences scattered across regions in ways that would have been economically impractical with slower transportation. A theater company could perform in multiple towns across a territory. Musicians could play a circuit of venues. Speakers could deliver lectures to organizations in dispersed locations. This increased exposure to external culture brought variety and cosmopolitan influence to communities that had been more isolated and locally focused. The environmental effects of this increased connectivity were complex and often contradictory. The concentration of economic activity in regional centers sometimes reduced the total amount of land dedicated to dispersed small-scale industrial or commercial uses, allowing some areas to revert to agricultural or natural states. But the accessibility that vehicles provided also encouraged development in previously remote areas. Scenic locations became sites for second homes. Resource-rich but isolated areas became economically viable for extraction. Wild areas became accessible to recreational users whose presence altered ecological balances. The pace of change itself accelerated as vehicle mobility allowed innovations and ideas to spread more quickly. A successful business model could be replicated across a region as entrepreneurs observed what worked elsewhere and adapted it to their own locations. Technical innovations spread through networks of practitioners who could visit each other and share knowledge directly, rather than relying on slower written communication. The compression of distance facilitated the compression of time in the diffusion of change, creating feedback loops where innovation bred more innovation at increasing rates. The global pattern was toward greater integration and interdependence, with regions that had operated in relative isolation becoming nodes in larger networks of exchange and influence. This integration was not without tension. Local cultures and economic structures adapted to external pressures that arrived more frequently and forcefully as vehicle mobility eliminated the buffers that distance had provided. The vehicle did not merely connect the world, it fundamentally altered the nature of connection, making proximity less about physical location and more about accessibility via the roads that vehicles traveled. The vehicle altered not just the mechanics of movement, but the relationship between human beings and the experience of space itself. Before mechanical transport, the journey between places unfolded at a pace that allowed observation of gradual transitions, the slow change in landscape, the incremental shifts in architecture and vegetation, the accumulation of small differences that marked passage through distinct territories. Travel at vehicle speeds compressed these transitions, reducing the journey to a sequence of destinations connected by intervals of motion, where the space between became less significant than the endpoints. This compression changed how people conceived of distance. What had once been measured in the effort required and the time consumed became measured primarily in hours and minutes of vehicle travel. A place 100 miles distant seemed closer than a place 50 miles away, if roads made the farther location more accessible. The psychological map of the world reorganized around vehicle infrastructure rather than purely geographic distance, creating geographies where some regions felt near despite being far, and others felt remote despite being close. The sense of isolation diminished for those with access to vehicles, creating a perception that anywhere was reachable given sufficient time and fuel. This perception of accessibility reduced the psychological weight of distance that had shaped human experience for millennia. The world seemed smaller, less compartmentalized into the local and the unreachably distant. But this reduction in isolation was not universally distributed. Those without vehicles or without access to adequate roads remained isolated, while the world around them became more connected, creating new forms of inequality based on mobility rather than purely on geography. The relationship between effort and movement shifted fundamentally. Physical exertion was no longer required for locomotion. One could travel great distances while remaining seated, expending minimal physical energy. This disconnection between movement and bodily effort changed the phenomenology of travel. The fatigue one felt after a long journey was mental rather than muscular, a result of sustained attention and decision-making rather than physical exertion. The body became a passenger rather than a participant in the act of traveling. The experience of landscape transformed when viewed through the frame of a moving vehicle. Scenery became something observed rather than traversed, a visual experience separated from the physical engagement of walking or riding through terrain. The speed of passage reduced the opportunity to notice small details, individual plants, subtle changes in soil or rock, the texture of specific places. What remained were broad impressions, memorable landmarks, the general character of regions rather than the specific qualities of locations. The world became more visually accessible, but perhaps less intimately known. Time acquired new textures shaped by vehicle travel. Waiting in traffic created periods of enforced stillness within journeys, frustration at being motionless while desiring to move. The experience of cruising along open roads produced a different temporal quality, a flowing present where distance accumulated smoothly and attention could drift without the constant negotiation that walking or riding required. The segmentation of time into driving periods and destination periods created rhythms different from the more continuous experience of slower travel, where the journey and the destination blended more seamlessly. The sense of control and agency that came with operating a vehicle influenced how people thought about their relationship to the world. The ability to decide on impulse to go somewhere and then simply go created a kind of freedom that seemed almost limitless compared to the constraints of scheduled public transport or the preparations required for animal transport. This freedom was bounded by practical constraints, fuel costs, traffic conditions, available time. But within those bounds, it felt expansive, a form of personal sovereignty over one's movements and decisions about how to use space. The social space of the vehicle interior created new contexts for interaction. Families spent hours together in the enclosed environment of a vehicle traveling to distant destinations, creating opportunities for conversation, but also for conflict in a space where escape was impossible. The vehicle became a site of negotiation between competing desires about routes, stops, and destinations. It became a private bubble moving through public space, a territory under the control of the operator where normal social rules were suspended or modified by the unique circumstances of shared travel. The democratization of mobility that vehicles promised existed in tension with the inequalities they created and reinforced. Ownership of a vehicle provided capabilities and opportunities unavailable to those without. Yet the cost of ownership placed it beyond reach for significant portions of the population. The infrastructure that made vehicles practical, roads, fuel distribution, repair services, received investment that might otherwise have supported public transportation systems that would have served those unable to afford private vehicles. The society that organized itself around vehicle transportation created disadvantages for those who could not or chose not to participate in that system. The environmental relationship shifted from one where human transportation integrated into natural cycles to one where it relied on extracting and consuming finite resources. The fuel that powered vehicles came from petroleum deposits formed over geological timescales, consumed in minutes of driving that converted ancient stored energy into motion and waste heat. This extraction created dependencies on resource supply and on the infrastructure to refine and distribute fuel, connecting everyday mobility to global systems of extraction and trade in ways that animal transport never had. The aesthetic of the landscape changed as vehicle infrastructure became dominant. Roads carved through terrain, following engineering logic that prioritized grade and curve over the contours of natural topography. The visual environment along routes acquired a particular character defined by signs, pavement markings, guardrails, and the architecture of service facilities. This aesthetic was functional rather than organic, created by human planning rather than emerging from the slow interaction of settlement and geography. Some found it ugly, a degradation of landscape. Others saw it as neutral infrastructure, barely noticing what had become so familiar. The attachment people formed to vehicles went beyond mere utility. A vehicle became an expression of identity, a personal space that reflected individual preferences and priorities. The choice of vehicle type, the care given to maintenance and appearance, the modifications and personalizations, all of these became ways of communicating something about oneself to the world. This emotional investment in what was fundamentally a machine seemed strange from a distance, but made sense within a culture where vehicles were intimately integrated into daily life and self-conception. The skill of operating a vehicle became a threshold competency that divided those who could fully participate in mobile society from those who could not. Learning to drive was a rite of passage that marked a transition toward adult independence and capability. The possession of a license and the ability to operate a vehicle competently opened possibilities and conferred status. The inability or unwillingness to drive marked one as dependent or as outside the mainstream in ways that created subtle but real social consequences. The risk of death or injury that accompanied vehicle travel became normalized, to the extent that societies accepted casualty rates that would have been intolerable in other contexts. Thousands died annually in vehicle accidents. Yet this toll was treated as an acceptable cost of the mobility system rather than as a crisis requiring dramatic intervention. The normalization of risk reflected how deeply vehicle transportation had embedded itself in the structure of society. The benefits seemed to outweigh the dangers, or at least the alternatives seemed worse or impractical to implement. The future orientation of vehicle culture created pressure toward continuous improvement and replacement. New models appeared annually, incorporating refinements and additional features that made older vehicles seem obsolete even when they remained functional. This cycle of innovation and planned obsolescence created economic activity and employment, but also generated waste as functional vehicles were discarded in favor of newer versions. The culture around vehicles valued the new over the enduring, progress over stability. The philosophical implications of this mode of mobility extended to questions about the good life and human flourishing. Did the speed and convenience of vehicle travel enhance human existence, or did it create a pace and pattern of life that was ultimately less satisfying than slower, more locally rooted alternatives? Did the freedom to travel anywhere translate into meaningful freedom, or merely into the exercise of choice without purpose? These questions had no definitive answers, but reflected deeper uncertainties about whether the transformation that vehicles had brought represented authentic progress or merely change whose ultimate value remained uncertain. The lived reality was more ambiguous than either celebration or critique could capture. Vehicle mobility brought genuine benefits and genuine costs, and individuals navigated this complexity according to their own values and circumstances. The trajectory of vehicle development pointed toward continued refinement of existing patterns rather than fundamental reconception of what vehicles were or how they functioned. Engineers worked on incremental improvements in efficiency, extracting more motion from each unit of fuel through better engine design, reduced aerodynamic resistance, lighter materials that required less energy to accelerate and maintain in motion. These gains accumulated slowly, each generation of vehicles performing slightly better than the previous. The progress measured in percentages rather than orders of magnitude. The materials used in construction evolved as new alloys and composites offered advantages in strength, weight, or cost. Steel remained fundamental, but was joined by aluminum in applications where reduced mass justified higher material costs. Plastics replaced metal in components where their lighter weight and resistance to corrosion outweighed their lower strength. Glass evolved to provide better insulation and safety, using lamination and tempering to prevent shattering into dangerous shards during accidents. Each material substitution required redesign of surrounding components and manufacturing processes, making change gradual and partial. Safety features accumulated as understanding of accident dynamics improved and as regulatory requirements mandated protection for occupants. Structures designed to absorb impact energy protected passenger compartments during collisions. Restraint systems prevented occupants from striking interior surfaces or being ejected from vehicles. Improved braking systems reduced stopping distances. Better lighting increased visibility at night. These features saved lives and reduced injury severity, though they could not eliminate the fundamental risks inherent in high-speed travel in vehicles sharing roads with other traffic. The comfort provided by vehicles increased through attention to details that reduce fatigue and improve the experience of travel. Suspension systems became more sophisticated, isolating occupants from road irregularities while maintaining handling precision. Climate control systems maintained comfortable temperatures regardless of external conditions. Seating evolved to provide better support during extended periods of sitting. Sound insulation reduced the intrusion of engine noise and road sounds. These refinements made vehicle travel less taxing and more pleasant, encouraging longer journeys and expanding the practical range people would travel for various purposes. Electronic systems began to appear in vehicles, using solid-state components to control functions previously handled by purely mechanical or electrical systems. Fuel delivery could be optimized by electronic sensors and actuators that adjusted mixture ratios based on engine conditions. Ignition timing could be varied to match load and speed. Instrument displays could present information more flexibly than mechanical gauges allowed. These electronic controls improved performance and efficiency while adding complexity that required new diagnostic and repair capabilities. The question of alternative power sources persisted in the background of vehicle development, never quite achieving practical viability, but never entirely disappearing from consideration. Electric vehicles offered the appeal of simplicity and the elimination of combustion-related pollution, but battery technology limited their range, and recharging took far longer than refueling. Hybrid approaches that combined different power sources attempted to gain advantages from multiple systems, but added weight and complexity. The dominance of internal combustion engines reflected their proven performance and the established infrastructure supporting them, rather than any fundamental superiority over all possible alternatives. Urban planning faced growing challenges as vehicle numbers increased beyond what existing street networks could accommodate. Congestion reduced the speed advantages that had justified vehicle adoption, creating frustration and wasted time. Parking consumed valuable urban space that might otherwise support productive activities or housing. Air quality degraded in cities with heavy traffic, affecting health and quality of life. These problems generated discussion about alternatives, improved public transportation, denser development that reduced travel distances, restrictions on vehicle use in central areas. But implementation faced resistance from populations and economies organized around vehicle mobility. The dispersed settlement patterns that vehicles had enabled created dependencies that made retreat difficult. People lived far from work because vehicle transportation made the commute manageable. services distributed themselves across territories because vehicle mobility made customers willing to travel to them. The entire spatial organization of commerce, residence, and recreation assumed vehicle access, and any significant reduction in vehicle use would require restructuring these patterns in ways that seemed impractical or undesirable to most people who had adapted their lives to vehicle-dependent arrangements. The environmental consequences of vehicle proliferation began to attract attention as accumulating evidence suggested that exhaust emissions contributed to air quality problems and potentially to broader atmospheric changes. The scale of fuel consumption and the resulting release of combustion products had grown to levels where local effects were visible and measurable. Whether this would prompt significant changes in vehicle design or use patterns remained uncertain. The economic and social investment in the existing system was enormous, and alternatives faced both technical challenges and cultural resistance. The global distribution of vehicle ownership remained highly uneven, with wealthy nations having far higher ownership rates than poorer regions. This inequality reflected broader economic disparities, but also suggested that as developing regions industrialized, the global vehicle population could increase by multiples, intensifying all the effects, positive and negative, that vehicles produced. The infrastructure to support this expansion would require investment that many regions struggled to afford, and the environmental impact of a vastly larger global vehicle fleet raised questions about sustainability that had no clear answers. The automation of vehicle operation emerged as a distant possibility, imagined by engineers who envisioned systems that could navigate, avoid obstacles, and transport passengers without human control. The technical challenges were substantial: sensing the environment accurately, making decisions in complex and unpredictable situations, maintaining reliable operation across varied conditions. Whether such systems would prove practical or desirable remained speculative, but the possibility suggested that the relationship between humans and vehicles might continue to evolve in fundamental ways. The cultural integration of vehicles into daily life had become so complete that imagining alternatives required substantial effort. For most people in vehicle-dependent societies, the idea of organizing life without personal vehicle access seemed like a regression to an inferior state rather than a viable alternative. The freedom, convenience, and capabilities that vehicles provided felt essential rather than optional. This psychological and practical dependence ensured that vehicles would remain central to how societies functioned, at least in the near term and probably well beyond. The architecture of cities continued to adapt to vehicle dominance, with new development incorporating extensive parking, wide streets, and separation of uses that assumed vehicle travel between them. Historic urban cores that predated vehicles faced pressure to accommodate traffic and parking, sometimes requiring demolition of older structures or substantial modification of street patterns. The tension between preserving traditional urban forms and adapting to vehicle requirements remained unresolved, with different cities making different choices about which values to prioritize. The industries that had grown around vehicle production, service, and support employed millions and generated substantial economic activity. This economic importance gave vehicle interests significant influence over policy decisions affecting transportation, land use, and environmental regulation. The alignment of these economic interests with the preferences of vehicle-owning populations created political dynamics that favored continued vehicle-centric development over alternatives that might be more efficient or sustainable, but would disrupt established patterns and investments. The question of whether the transformation that vehicles had brought constituted progress or merely change without clear direction remained open to interpretation. The benefits were real and widely distributed. Speed, convenience, flexibility, access to opportunities and experiences that would have been impossible with slower transportation. The costs were also real. Environmental degradation, resource consumption, accidents, the restructuring of communities in ways that some found alienating or damaging to social cohesion. Different people weighed these factors differently according to their values and circumstances. The future would likely bring continued evolution rather than revolution, with vehicles becoming gradually more efficient, safer, and capable, while remaining recognizable as refinements of the basic pattern established in the early decades of their development. The fundamental relationship between human beings and mechanical mobility seemed stable, unlikely to change dramatically absent some external forcing that made the existing system untenable. Vehicles had become part of the infrastructure of modern existence, as essential and unremarkable as electricity or running water, their presence taken for granted by those who had never known a world organized differently. The story of how they arrived would fade from active memory. And so, the narrative of this assembly comes to its quiet conclusion. Whether you are still awake, or whether you have already drifted into a deep and peaceful sleep, know that you are exactly where you need to be. The world is vast, but tonight, its systems are simply the backdrop to your rest. Thank you for joining me here at Quietly Made. Rest now. Join us again tomorrow. Good night.